Hey everyone, so here's 7 in class. 7 in class is going to be a worksheet and it's going to be some practice with average value. Um, yeah, and maybe even a little something else, but we'll see when we get there. All right, well let's start with this. I notice it says must do, so no, really you must do this one. Yeah, in fact, I think before I write all over it, I'm going to take a scan of it because I don't know if I have any more of these. Okay, certainly not at home with me. Next. All right, so we're going to start here with this, and it says average value connected to average rate of change. So I want to dig some more into that that issue that we were dealing with in the last video. And by last video, I mean in the video for assignment 7. Okay, so now I'm going to do it here. And in the pen. Oh, I got a pen. Okay. Find the average velocity from the graph of velocity. We've been given velocity from 2 to 5. So I want the average velocity from 2 to 5. Remember, this is the velocity graph. There are an infinite number of velocities from 2 to 5. The velocities are all these heights. You know, it's as if we had our little pet squirrel checking how fast are we going, how fast are we going, how fast are we going, how fast are we, and writing them all down. And now we want to know what's the average velocity that we had from 2 to 5. Okay? Well, so I'm asking you for the average value of this function that I've given you. And the average value of this function that I've given you is going to be 1 over 5 minus 2 integral from 2 to 5 of v of t dt. Mr. Kukla, do I have to write the equation for this? No, you do not write the equation of this velocity function. And no, just count the areas. Look, each of these boxes has a width of 1 and a height of 10. 1 times 10 is 10. So 10, 20, 30, 40, 50, 60, 70. This is half a box, this is half a box. That makes another 10, 80. And here, this is 2 boxes cut in half, so there's another 10, 90. So the value of the integral from 2 to 5, I got 90. Because I added up the area of all these boxes. And that's exact. It's not an approximation. What's that area from 2 to 5 under the velocity curve? 90 times, what do we have here? 1 over 3, and so I get 30. The average velocity is 30. If my units here were feet per hour, this would be 30 feet per hour. If my velocity was meters per second, this would be 30 meters per second. We know the average velocity is the average value of the velocity graph. Okay, now check out what we're asked to do. Construct a graph of s of t using the fact that s of t is the integral of v of t. And we know that because we know that v is also called s prime. And if we find the antiderivative of s prime, that's going to be s. We're also told that s of 0 equals 0. So let's see what we can make of this. Let's see how we're supposed to understand this. I can make a position function from velocity. Sure, I know my initial position. My position at time equals 0 is 0. Then I look over here and I say, okay, velocity from 0 to 1. Well, I got some area here. 1 up, a 1 over, and 10 up. So I'm going to say 1/2 1 minus 0 times a height of 10. And so what do I get? I get 1 times 10 divided by 2 is 5. Okay, and if I'm doing meters per second times seconds, then I'm going to end up with meters when I find that area. So these are meters. Position graph, 5 meters at 1. Doink. It's not an area. It's an area on this graph. It's a y value on this graph. In fact, I could take this a little further and say, hey, isn't it the case that if I were integrating velocity, v of t dt, that would give me s of x minus s of 0, because the antiderivative of velocity is position, and I want to evaluate that antiderivative at x and at 0. We were just told that s of 0 is 0. In other problems in the future, s of 0 will be some other number, like 5 or negative 2. But for our problem, s of 0 is 0, which really means that s of x equals the integral from 0 to x of v of t dt. Okay? So, if I integrate v of t from 0 to some point, that total area that I'm getting, that's going to be my y value for that x. So, when we integrated velocity from 0 to 1, and we got an integral value of 5, that means that if this integral was equal to 5, then s of 1 is 5. And so let's say what we mean. We mean s of 1 is equal to the integral from 0 to 1 of v of t dt, or you could understand that as the integral from 0 to 1 on s prime dt. So when I do this integral, when I find the area under this curve, I'm finding s of 1. Really, I'm finding s of 1 minus s of 0, but s of 0 is 0 in this problem, so I got s of 1 minus 0. So if I integrate velocity, I'm getting this position value. That's why here on my position graph, I marked a point 1, 5. The value of the integral was 5, and the time was 1. So at 1, I had a position of 5. Now, we can proceed in one of two ways. The way we've defined things here, first, we've said, okay, if I want to now know what position at 2 is equal to, that's going to be the integral from 0 to 2 of v of t dt. Okay, the integral from 0 to 2, why, that's this triangle. And how will I find that integral? How will I find that area? Well, it's 1/2 base of 2, a height of 20. These cancel, I've got 20, so I know that s of 2 equals 20. And how is that important? Well, at 2, I'm making a part at 20. Great. What about s of 3? 3. 3. Well, now I want to integrate from 0 to 3. Okay, so integrating from 0 to 2 is finding this area. Integrating from 0 to 3 is finding this area. So we have half a box and half a box. That's 1, 2, 3, 4. And here's another half of 2 boxes. So 5. Let's just confirm that. Half a box, that's 1, 2, 3, 4, 5. Good, but remember, 5 of these squares whose area is 10. So 5 times 10 is 50. So when I plug in my 3, I get s of 3 equals these areas. We have 1/2 plus, I guess that's 1.5. Yeah, I don't want to do it that way. I just want to count the boxes and say, that's 50. And I just want to make that mark that says, that's 50. What I really wish I could do is just use one area formula here, but I can't, because this isn't a triangle. This is a trapezoid. This is a triangle. And I just can't use just one formula. So maybe I want to think about doing something a little different. Like I was able to get that 50 and plot that at 3 will be at 50 moment. But I really think that I want to do this problem a little differently, because what we're doing with this definition, we're always starting at 0 and going until where we want to stop. But what if we didn't always start at 0? What if we thought about this S of 3 thing? What if we thought about that as saying, well, couldn't I find just this area and then add it to the answer I had before? Yeah, I really could do that. I really could say that S of 3 is going to be the integral from 2 to 3 plus this S of 2 value. And if I move that over here, I'm looking at S of 3 minus S of 2 equals the integral from 2 to 3 of v of t dt. Well, that makes a lot of sense to me. If I find the antiderivative of this, I'm going to plug in a 3, I'm going to plug in a 2. The antiderivative of velocity, well, it's position. I'm plugging in a 3 and I'm plugging in a 2. So really, we could say then that if I find the integral from 2 to 3, that's just that one little strip, and add what I had before, I get my new value. And I think I'm going to do that. I think this was 20, and what's the area under the velocity curve from 2 to 3? Well, from 2 to 3, I have this trapezoid. How do I find the area of that trapezoid? I do 1/2 height times base 1, 20, plus base 2, that's the base, that's this length here, 40. Okay. 3 minus 2 is 1, so that's going to go away. 20 plus 40 is 60. 60 divided by 2 is 30. So 30 is the area from 2 to 3, plus the area I had before, 20, and therefore I get S of 3 equals 50. Okay, great. Now, let's say we want to find S of 4. Well, S of 4 is going to be the integral from 3 to 4 plus S of 3, right? Add that previous amount to the next strip. My next strip goes from 3 to 4. 1, 2, 3.5, or 35. So this is 35, this was 50, and I get S of 4 is going to be 85. You could, of course, say, hey, I'm looking for the integral from 0 to 4. But, you know, that's 3 different things. I got to find this one, I got to find this one, I got to find that one. And instead, why keep adding up this area again and again and again? Why not just remember it from the last time we used it and add that to this? So maybe, while we could imagine this as 0 to 4, we could say, let's take what we had the last time and add the next strip. Let's take what we had the last time and just add that next strip. And that's going to be kind of important for us. 85 at 4. So 4 going up to 85. Okay? What about 5? Well, for 5, now I'm integrating from 4 to 5, and I need S of 4. Well, that means that S of 5 is going to be the area of the new strip plus, what was S of 4? 85. Okay, so what's the area of the strip from 4 to 5? From 4 to 5, I've got 10, 20, 25. So 25 plus 85, S of 5 is 110. And therefore, I've got at 5, 110. And so if I connect these dots, that's going to give me a graph of S of t. Now I have my position function. This is very labor intensive. But This is really important in two ways. One, to answer this question. But second, in Chapter 7, we're going to be saying this a whole lot. My ending position minus my starting position is my change in position. Or S of x equals S of 0 plus the integral from 0 to x of a of t dt. If I add my starting position to my change in position, I get my ending position. We're going to do that a whole lot. And this is me just adding strip after strip after strip. Okay? So I want to be able to think about that this way. But wait, there was one more thing here. Find the average velocity using your position graph. Well, this is a position graph. An average velocity is represented, and remember, we're doing from 2 to 5. 2 to 5. We want the average velocity using position from 2 to 5. Well, what did we say average velocity was given the position function? We said that average velocity was going to be S of 5 minus S of 2 over 5 minus 2. S of 5, well, according to my graph, S of 5 is 110. S of 2, according to my graph, is 20. Over 5 minus 2 is 3. I get 90 over 3, or 30. Average velocity is 30. And what happened when we did it with the velocity function and the average value of this? We found that this area was 90, and we did 1 over b minus a times the value of the integral here, which was 90, and we ended up with 90 divided by 3, or an average velocity of 30. Wow, there's a lot here. Average velocity as an average rate of change, average velocity as the average value of that velocity equation. Wow. Okay. Woof. You know, I think it was 2 years ago, maybe 3 now, where there was a problem very much like this on the AP exam. It wasn't quite so labor intensive, but it was, I had to think about this change in position being what my original position was, plus the adding this additional strip to it. This strip of area corresponds to this change in y values. This strip in area corresponds to this change in y values. And that's, I think, what I was really trying to say there. That this strip in area means this change in y values. All right. Now, what were the other things I wanted to do? Well, I want to make sure that you can do some of this average value stuff with your calculator by hand. I'd like to have a little more practice with this. I also want to see if we can say something about finding when the function takes on its average value. Okay, so let's have a function, and my function f of x, or perhaps p of t. That's the number of pes per minute is the output, and the input is minutes. And if you don't know what pes is, you should probably Google that, because most of you know what pes is. And really, who doesn't like a pes? All right, so I'm going to have a p of t function. It's going to be negative t squared plus 4t plus 12. Now, from our algebra experience, we know this is a parabola that opens down, and it's a parabola, and it's got a y-intercept, or in this case, a p-intercept of 12. So my parabola looks like that. When is this parabola equal to, when does it hit the ground? When do I have this 0 here? Well, let's factor out that negative t squared minus 4t minus 6. And I'm thinking that this is t minus, oh sorry, that was a 12. T minus 6, t plus 2 with a minus in front. Well, my t-intercept is 6. And if it mattered, there'd be another one over here at negative 2. But I'm not using that. I'm just looking at this one. Okay, so here's my p of t function. And you know, I can see that this is pes per minute. And I've got a different amount of pes per minute at time equal to 0 than at any of these places. In fact, I think it's safe to say that at every moment in time, the rate at which we're eating pes per minute, is changing. These lengths get longer, so I'm eating more pes per minute. These lengths get very small. In fact, I'm done eating pes, thank you very much, with 0 pes per minute. If I add up all of these pes and divide by my interval, I'm going to end up with the average pes per minute. And so I'm thinking, what's the average value? What's the average rate at which I'm eating pes? Yeah, no problem. That's 1 over b minus a integral from a to b of negative t squared plus 4t plus 12. Okay, this is going to give you my average pes per minute. So this will give me the number of pes that we consumed, and then we'll be dividing by these minutes, and we'll get pes per minute. Okay, because we're looking for where is the average height here. And maybe it's, yeah, I'm not sure where it is yet. So we've got an infinite number of heights, and I'm looking for the average of all those heights. This is what I'm going to find here. So I've got 1 over 6. Now, I need to integrate this. So the antiderivative of t squared is t to the third over 3, and there's a negative, so don't lose that. Why am I over 3? Well, if I take the derivative of this, that 3 comes down. Yeah, I don't see a 3 here. So there must be something present in the original function, so when that 3 comes down, it goes away, and I'm left with just t squared and that negative. Plus, what's my antiderivative here? Well, the antiderivative of t is t squared. If I bring that 2 down, I'll have a 2, but I got a 4 here, so there must have been a 2 already. Plus 12t. And I want to evaluate this antiderivative from 0 to 6. Okay? So what do I get? If I plug in a 6, I get 216 over 3 with a negative in front. So isn't that 72? I think it's 72. Let's check. Okay. I've got 6 to the third. 216 divided by 3, 72. So there's a negative 72, plus 6 squared is 36 times 2 is 72, plus 12 times 6 is 72. And that's an awful lot of 72s, but these cancel and I'm left with 72. Fabulous, 72. But we're not done yet, because now we have to plug in a 0. And I plug in a 0, I plug in a 0, and I plug in a 0, and I'm going to get 0. Now, please, humor me on this one. This won't always be 0. So get in the habit of plugging that thing in. Because if you're in the habit of not plugging that number in, then you won't plug the number in when it's not 0. So watch out for that. So we've got this, and out in front, I got 1/6. 1/6. So 72 over 6, or 12. 12. Well, wait a second. Wasn't that height? And so it turns out that is the average height. So, supposedly, if I had drawn this to scale, this area here, this white stuff, and this red stuff would be the same amount of area. Because, remember this part? Remember how average value 1 over b minus a, integral a to b of f of x dx was equal to f of c, that was our average height, times b minus a. Times b minus a? No. Sorry. The average value is equal to the average value formula. Now, if I multiply both sides by b minus a, I have f of c times b minus a equals the integral from a to b of f of x dx. So the area under the curve is equal to this area of a rectangle whose height is the average value and whose length is b minus a. So b minus a times f of c gets us this rectangle, and that rectangle has the same area as the area under the curve from a to b. Okay. Wow. There's a lot of stuff here. So, are we done with that one? I think we're done with that one. Yes, we did that. Yes, we did that. Oh, you know what we didn't do with this? We didn't do average rate of change. We just talked about the average value of pes per minute. So, well, let's do average rate of change. I want to know, and I'm still talking about this p of t function, negative x squared plus 4 times, it'll be big one day, negative t squared plus 4t plus 12. Okay, so I have pes per minute as a function of minutes. Great. And I want to know the average rate of change in p on 0 to 6. Okay? So I want the average rate of change. Well, the average rate of change is the slope of the secant on this graph. The slope of the secant on this graph is going to be p of 6 minus p of 0 over 6 minus 0. If I plug a 6 in here, negative 36 plus 36, I end up with 0. If I plug a 0 in here, I get 12. So 0 minus 12 over 6 minus 0, I get negative 2. So the average rate of change here is negative 2. And remember, the units on top are pes per minute, and the units on the bottom are minutes. And so what are the units on this negative 2? Well, decreasing by 2 pes per minute every minute. So let's say at time equal to 1, I had 5 pes per minute. Then I go down 2. So 1 minute later, I'm now at 3 pes per minute. Okay, it's a change in the rate at which we're eating pes. Nice. So there's the average rate of change in p. The average value of p was, I don't remember what it was now. I know we figured it out. Oh yeah, it was 12. 12 pes per minute was our average. That meant sometimes we were eating more than 12 pes per minute, and sometimes we were having less than 12 pes per minute, but our average was 12 pes per minute. All right, so here's the last that I want to look at with you, and I think you should do this with your calculator. F of x equals x to the third plus 2 on 0 to 2. Okay? A, find average value on 0 to 2. And to speed things up, I encourage you to use your calculator. Okay. Go try that. Tell me what you get when you come back. So, how'd it go? I want the average value, so I want 1 over 2 minus 0, integral 0 to 2, x to the third plus 2 dx. Great. And I know I can do this by hand. The antiderivative of x to the third is x to the fourth over 4. The antiderivative of 2 is 2x. And I want to evaluate from 0 to 2. So if I plug a 2 in, 2 to the 4th is 16 divided by 4. 16 divided by 4 is 4. And if I plug in a 2, 2 times 2 is 4. And don't forget, I want to plug in 0. 0 plus 0 is 0. Okay, so what do we get here? 4 plus 4 is 8, times 1/2 is 4. The average value, 4. Okay, but I asked you to do it with a calculator. And were you able to do it with your calculator? Let's check. We've got 1/2 times the value of this integral. So f int, and what's my function? X to the 3rd plus 2, close parentheses, no, comma, I'm on an old school calculator, comma x, comma a, comma b. So again, old school, function in terms of x, a value, b value. You don't have to put the function here. You could put the function in y1 and then put y1 here. But when I hit enter, I get 4. Okay? I need to be able to evaluate an integral with my calculator. In order to find the average value using my calculator, I needed to be able to use my calculator to find the value of this integral and then multiply by 1 over b minus a. Great. Let's ask the second question then. If we know that the average value is 4, when, what x, does f take on this average value? I mean, if I think about it graphically, I'm thinking about the x to the 3rd graph shifted up 2, and I'm going out to x equals 2. So there's 0, 2. If I plug a 2 into the function, I get 10. 2, 10. And I see an infinite number of heights here. And one of those heights, between 2 and 10, in fact, the one probably over here, we're going to call that, I don't know, but this length, this average value, that average value is 4. So I want to know when, what x value, this function takes on the average value that we just found. We found that the average value is 4. When does this function have that y value? Well, no worries. We can figure that out. So we know that the average value is equal to 1 over b minus a, integral a to b. Oh wait, I don't need to do that. Sorry. I'm looking for the place where the y value is 4. The y value on that function. Thank you. That's exactly what I was looking for. I want to set my function equal to that y value and solve for x to find out when that function, what x value, gives me a height of 4. So if I subtract 2 from each side, and then I take the cube root, I found out that when x equals the cube root of 2, so here is cube root of 2, at that moment, this function takes on the average value. Okay? Maybe one more of those? I think one more of those, and then we'll stop. Okay, how about this one? Find the average value of f of x equals x squared minus 1 on 0 to root 3. All right, give it a try. Come back when you're done. Welcome back. So I'm looking for average value, so I use 1 over root 3 minus 0, integral 0 to root 3 of x squared minus 1 dx. Okay, so that's 1 over root 3 there. Now, what's the integral of this going to be? The integral of x squared is x to the 3rd over 3, and the integral of negative 1 is negative 1x. I want to evaluate this from 0 to root 3. Okay, so if I plug in a root 3, I can have root 3 times root 3 times root 3, which is 3 root 3. 3 root 3 over 3 minus root 3. Minus what happens when we plug a 0 in here. Well, I get 0 minus 0, which is 0. Ooh, that's also 0. Ooh, says little Pikachu. Okay, so 0 times 1 over root 3 is 0. The average value is 0? That's the average of all the heights from 0 to root 3? Well, let's take a look and see what's happening here. We've got y equals x squared minus 1. This is 1, 0. Over here we've got 2. And so here's going to be my root 3. So we're saying, what happens when you add up all these negative heights and all these positive heights? Well, the answer is you get an average height of 0. Wow, well, that's kind of cool. Okay, so the average height from 0 to root 3 is a height of 0. When I add up all these negative heights and all these positive heights, the average height is 0. Really? You don't see the Pikachu here? I see the Pikachu there. All right, now, when does this function take on this average value? Say 0 equals x squared minus 1. Why 0? Because that was the average value that we got. So x equals 1. And think about it. You've got this here. And what am I saying? I'm saying, oh no, average value. Yeah, there's that average value, and it happens at 1. Good. All right, I kind of want to ask you, since we just did average value, I kind of want to ask you what's the total area. I also want to ask you what's the average rate of change. But I'm not gonna. But maybe you should. Instead, I'm going to say, I hope you have a fabulous day. It was great getting to be with you again. Take care.